Good morning, my name is David. I'm with the company Blackheart Technologies. We're down in Australia. I'm here today to present a solution from WavePro. It's a custom DK PTFE filled with ceramic, anything from 2 to, at the moment, 12 DK. They're working on solutions that's up to 15, and there's also a future plan for 20 DK. There's also investigations for getting the DK down below 2, as is quite phenomenal for PTFE, so 1.8 up to 20, that's the future plan for the actual PTFE with ceramic filling. Just to give you some context of who I am and what the background is to my interest in this, as I said, I'm David from Blackheart Technologies down in Australia. We are an antenna design company, also a cable supplier. What we do is basically antenna design, as I say, a passionate team of engineers. What that means for us is that we actually take our designs very serious, although we are very passionate about it. We look at all sorts of solutions and applications. The focus is on creative solutions. The idea with creative solutions is that it's not always going to be the complicated solutions or solutions that looks very fancy. It's all about back to basics, back to fundamentals. In doing fundamentals, we look at, for instance, a dipole. We take the dipole as the element and the building block, going further with the actual design that we then use. We, at the moment, have an exposure of a wide range of frequencies, currently from FM up to X-band, so 100 meg to 10 gig. Our biggest focus is obviously on 4G and Wi-Fi in our space, meaning that 700 meg up to 7 gig, which gives us Wi-Fi 6E, is the primary focus of the work that we do. High-end custom design, the focus is definitely, we know companies such as pointing antennas, companies such as Alpha Wireless and so forth, they do Wi-Fi well, they do 4G really well, they do marine antennas really well. For us, we don't then pay attention to those markets. We don't feel it's necessary to actually promote any effort into that application. We go for custom design, so we have customers who have their need for those type of antennas in their setups. So we focus primarily on customization of existing antennas and new ideas into a product. We also do have a website, e-commerce, rfshop.com.au. Gives you the opportunity to buy the off-the-shelf items, custom coaxial cables and routers and modems. But it's also where we will find the Blackheart Technologies antennas that we will then apply onto the website for you to buy, not just in Australia, but anywhere in the world. So a quick design example. This is just an example of the kind of thing that we can do, and the message is more specifically to tell customers antennas can actually be cool. So what we have here is, it's just a standard Wi-Fi omni antenna, so a dipole. But dipoles don't always have the performance that you need. In our case, what we do is we convert the dipole to a directional antenna. We add some directors, so that's basically a Yagi conversion of an existing antenna. The idea is, though, that you need to have the antenna look more like something that people want rather than something need. So in this case, the antenna, it performs really well. As you can see, it has a gain now of 7.3 dB for what was a 2 dBi antenna. But for anybody that's more visually interested in what's going on with the antenna, actually is a flag. I have the Australian flag on there because that's where we come from. You can do exactly the same with a US flag or any flag. So if you have any specific banner or any type of logo you want to present, that is possible. And the antenna performance, and also presented on YouTube on our channel, is always available. It's about the message, it's about creativity, it's about getting RF principles out to the market. That gets us to the next point. And that's really, what are we doing with WavePro? Why is Blackheart Technologies excited to be aligned with WavePro and presenting this solution as a new idea that could potentially make big waves in the actual market? What we have is a PTFE Teflon infused with ceramic that gives you now variability, so that you have a DK that you can choose as a designer. So as a designer, you could say, I need a DK of 5 or 6 or 7. You don't have to go to a stock item that's anywhere. You can say, I really wanted to have something right in between what's currently available. You come to WavePro, they can help you to get that material exactly the way you want it. As I can show here, it's currently, the scope is 2 to 12. That's currently a scope that is realistic solutions. There's future plans for 15 and 20. And also going lower to 1.8. So the scope of what can be done with the PTFE is, for us as designers, it's a whole new world. It gives us complete freedom for where we want to go. Now, as I say, it's made to order. the other thing here is we're going into this whole digital world, so made to order means that you can come to the company gives you the options that or listens to your needs and then takes that further with you. As I mentioned earlier, it's panel thicknesses, but there's also shapes and different configurations that you can do. Brings me to what you can see there and on the screen. So of course panels is the easy one. With panels, think about PC boards, think about shaping. WavePro, as part of the Galo company, has decades of experience in actually making materials. So shaping is actually not an issue at all. You don't have to think in panels, you can think of any shape or size that you have. Now what I have in my hand is a disc with a funky shape. I'll just bring it onto the camera. As you can see, it's just conformally shaped and complete new 3D shape. So as a an antenna designer or somebody that's more focused on RF and antenna design work, part of the complexity is how can I do my mechanics? What can I do to shape this material that I see on paper into what I need? Going to manufacturers, going to somebody that helps you buying a billet or something of material and then shaving off half the material. In this case, come to WavePro from the start, say this is the shape I need, and that's the solution that you will get at the end. Metallization, the next topic here of course is also metallization. So it's not just about the dielectric that you can insert into an antenna, you can use it as the whole antenna integration as well. What I have in my hand is a planar LPDA or printed log periodic dipole array. It's metallized, so the whole antenna comes from material that is the PTFE, and on top of it is actual metal layer, so the antenna as is gets delivered from WavePro to your need. There's other materials as well, so whatever your requirement, do come to WavePro, have a discussion with them about the metallization for the actual final solution. It goes without saying, the benefits of high decay, and that's part of the presentation that I will go in a little bit further to actually explain what you can do with the decay in terms of antenna applications, in terms of general applications. There are more that you can think of, so the idea with the whole presentation and where we're heading with this is it prompts you to think more about what can be done. So if what we say here is useful, if it is actually, can you also do something else with it? Please come and talk to the team here. In the slide there are a few things that we actually don't include that we learned through the course of IMS2022, and I'll mention them as I go through that further. Typical ideas and ways that you can apply the actual material. This is leading into my slides as well. Stack antenna or patch antenna, so of course that's always based on a printed board material. Getting a decay in there, either below or on top as super straight, that all has design benefits, which I will run through and show you. Dielectric resonator by itself, that of course needs a dielectric that you can use. Various types of antennas, having the ability to now have a variable epsilon R or decay value gives you that freedom further. Radomes, not necessarily one of the highlights of what can be done, but it's very important, and the higher we go in frequency, the more detail we need to have in the actual properties of a radome, using the detail and having the thickness ability, and also working on environmental robustness of this type of material, and the end use from WavePro is certainly something worth considering. And then dielectric lenses, probably the topic that has the most benefit for a designer, thinking about limits potentially in bandwidth or applications, having another variable that you can use, which is the decay from a very low value to a high value as you want it, is something that needs to be considered. Now, first example is the one that I showed just earlier, the printed LPDA or log periodic dipole array. This antenna, it's been published, and this is a replica of the actual paper, but it's not using the material by name that was used in the paper itself. We took the actual properties, we designed the antenna on the equivalent material, that is this one, with the same thickness, with the same decay material, and it's a fully functional antenna using a direct equivalent of the material used in the paper. You can see the antenna itself, it is working. This is as per simulation by doing CST. It's radiating. In the example, the radiation that we're showing there is at 5.8 gigahertz. So it is radiating, it's behaving well. And the plot that we show in terms of the actual radiation pattern is an antenna that's bidirectional, so it goes up and it goes down, and has a gain of, let me just see there, 5.5 dBi. So it's 5.5 dBi up and down and through the whole band. So this antenna specifically, just for an example, is designed to go from 500 megahertz up to 7 gig eventually. That's the long-term plan. Now, as I mentioned earlier, stacked patches, it's something that actually comes close to heart for myself. So this example that I have here has no extra material in it. So this is the baseline antenna, just to show what can be done with it. So as a baseline antenna, this is a significantly big patch that we designed for ourselves about 2 years ago in a 4G application. It's meant to work at 700 megahertz. We weren't quite there yet on this specific example, but we were limited with the size that we could use for the antenna. It's a MIMO concept, and the patch gain was only 4.3 dBi, which in antenna patch terms is not huge. It's okay, you can work with it, but you expect something more in the order of 5 to 6. Adding substrate and adding a superstrate, which are the two elements we did both in this example. First of all, by adding the substrate with the variable layers that we had, actually a bit of a deviation from the notes, we use various layers. So it's not a single layer slab. We now had the freedom to go through a bit of a layer from a low decay, high decay, and highest decay under the antenna to build up the whole behavior of the antenna. So you can see the frequency shifted. It was high, and then we just, because of the decay underneath the substrate, in addition to the original FR4, we now have an antenna that works from 600 megahertz up to 750 megahertz, so significantly lower for the same size. That's not the only thing that changed though. Because of the superstrate we put on top, just switching back again, so we had the original antenna 4.3 dBi, as I mentioned. It's workable, it's an okay radiation pattern, but with the superstrate on top of it, we actually increased the gain, the forward gain, by beam shaping the actual antenna outcome and performance to 7.6 dBi. So two aspects of the antenna that we were actually to manipulate and improve just by using material at the top and at the bottom. Now, what I want to mention here is something that's, you need to think about this from two different perspectives. First of all, the thing that comes to mind is antenna miniaturization. We make the antenna smaller by adding the actual material below the antenna, so that's obviously the obvious way of what we're doing. But also, if you could have certain fixed dimensions. So, well, I have an antenna that can only be 300 by 300 millimeters square. That's basically what this one is. You want to get better performance, and that's where you can actually add material. So it's either you make the antenna smaller, or you can say, this is my dimension, I can make the antenna bigger. So you actually electrically, considering the electrical properties, the antenna is bigger than it was before. Hence you get the higher gain and a better radiation pattern for the same baseline material and mechanics. Another example, as I mentioned, is dielectric resonators. So the dielectric resonator used in the original slide is basically a dielectric block that you excite to radiate. Another way to look at it is a monopole that gets dielectrically loaded. The loading is a disc or a tube that needs to be slit over the monopole itself. It gets better if you can have variable values going through, so not just a fixed block over it, but basically from one decay to another one to another one. In the options that you have from 1.8 to 20, you can use that. You can really have a smooth gradient from one value through to a next value, getting an antenna such as this that works from 100 megahertz up to 300 megahertz in a single monopole. That kind of bandwidth you will never get from a single dipole structure. Adding these loading elements is actually going to help you to get a phenomenal result using the same baseline antenna, just adding more material and getting the result. As you can see from the field distribution and the radiation pattern, it behaves really well. It has a clean shape, it has a clean pattern, and the gain is actually pretty high at 4.46 dBi gain. I mentioned earlier, Radomes. It is a design aspect that needs to be considered, and the higher we go in frequency, if you think about millimeter wave, the radome is critical in not breaking the antenna, but still protecting it. Having exact material properties and having knowledge of that, and even control of what you actually want to use, is a feature and an artifact that can be used. Coming from Australia, radome is seriously important because we have a lot of solar and sun and protection that we need. You can see recently was a lot of storms, so it's not just for sun, it's also for water. That's part of the design. This example is not, it's a thin shell, so as you can see, it doesn't do much to the wave, which is also sometimes what you just need. It's safety and protection. Dielectric resonators, as I mentioned earlier, millimeter wave, that's another application. The low loss aspect of the PTFE, something that needs to be considered here. By low losses means you have this dielectric resonator, you're not losing all your power in your material, you launch it, you shape the beam, and you get an antenna at the end of the day that comes out and a gain of 16.8 dBi. And you can see the impedance match of this type of shape using just type of material from PTFE, 60 gig up to 100 gig, and it's well matched, well behaved through the whole band. Useful for millimeter wave applications, automotive radar, and those type of applications. Now, the last two examples, that's really where a lot of freedom is now added, so more variables, adds more opportunities. First of all, as I mentioned, the shapes. So we have the shaper's head. Machining the lens is one thing, can be done out of the factory. Also, you're not stuck to certain values, PTFE of 2 or so, you can actually change that. So if you say, I want this specific type of lens, but it needs to be thinner because I can't have it that big, it doesn't fit, increase your decay, and then get a smaller lens for the same effect. That's the kind of thing that now is possible. This is just a classic horn antenna with a final gain of 17.7 dBi, with a lens that acts as a radome and protection. Also, some applications that was discussed here at IMS is, for instance, in a hygienic application where you actually need to look at the whole system with a vacuum seal, everything. All those aspects is part of the solution package with WavePro and Garlock as a company behind them, that really full turnkey solution, not just a mechanical PTFE and doing something that you don't know, is the PTFE going to work? Talk to Garlock because they have the expertise on years of history with the actual material itself. Then the last one that is actually really an interesting one, Lunenberg lens. So the complexity for us as antenna designers is, we know this is really fancy lens, we love the lens itself, but how do you make it? How do you actually get something made that has one decay in the middle, then another decay layer on top, just like an onion? It has all these layers on top of each other. This is the beauty of talking to a company that has decades of experience in building materials such as this, with various types of material embedded into one solution. You can create a Lunenberg lens that has that property. Again, there's just an example of this lens specifically applied to the horn antenna. An antenna again with 17.8 dBi. The Lunenberg lens, it's an awesome antenna, awesome solution. With the help of WavePro, can be done quite easily. And then, in conclusion, as I mentioned, dielectric substrates, as we know, antenna engineers, it's a fundamental building block. Having control of that building block gives you control freedom at the end to do more with it, rather than just say, this is off the shelf, put it in there. Bandwidth improvement, specifically thinking about what I did with the dielectric resonator, the monopole. Size reduction. With the patch antenna, there's the two aspects to it: either make the antenna smaller or make it look like a bigger antenna by adding the material, getting you either better bandwidth, smaller or lower frequency, or better gain, or all of the above. Environmental protection, basically a radome. Beam shaping, again, super straight or the dielectric lens, including the Lunenberg lens. Physical support, if you want to have something that is strong and rigid, but it has to have a low decay. In my case, imagine if I have an epsilon R of 1.8, that is much stronger than building a piece of foam in there. If I just have a little bit of a decay, it will help a lot. As I said, Blackout Technologies, quite pleased to work with the team at WavePro on this specific solution. If you have any questions, if you have anything specifically that you want to see how this gets applied, we use design software CST, so we can model and integrate this all virtually for you, being remote in Australia or anywhere in the world. Happy to help. And lastly, WavePro offers custom PTFE material with low loss characteristics. Please contact the team at WavePro if you have any further information. Go to their website, you can order samples on there, and we'll take it from there. Thanks a lot.